All right, so let's start with where we left off last time, right? So what did we do in the last class? We discussed a sequential breadth first search algorithm, right? Based on frontiers, right? So what was frontiers? Basically, we maintained the set of vertices at the current level, and we built a set of vertices to be processed at the next level, which we called the next frontier, right? And we figured out how to add vertices to that set, and eventually we replaced the frontier with the next frontier and started the next iteration. Yeah, so that was the sequential algorithm, and then we identified some opportunities for parallelism. And then we discussed an OpenMP based code, right? So this is a shared memory based code, right, where the threads share the same global memory. So any processor can access any information, right, in the memory. So any data structure, right? So we're assuming, of course, that these data structures, most of these shared data structures are obviously not on the stack, right? They are allocated from the heap or globally declared, right? And then we discussed that how do we implement this in parallel? Well, we maintain something called a local next frontier. And what each processor does is it processes some of the vertices in the frontier, right? A subset of them. All the vertices in the frontier are divided amongst the threads, right? And each thread basically works on its own set of nodes in the frontier. And it basically processes the neighbors and adds them to something called the local next frontier, right? Instead of a global one. And at the end, it basically just merges that local next frontier into a next frontier, right? And then this next frontier is used as the local frontier for the next iteration. All right. And we discussed some ways of implementing this, that within the core loop where you're doing a lot of processing and a lot of operations are being performed, you want to basically use atomic instead of critical sections. And at the end, when you have to do these merge operations, which are only done once, right, at the end by each thread, there you can use critical, right? And then we discussed some efficient ways of implementing this merge operation. Okay. All right. So today we are going to get into distributed algorithms, right? So we are going to talk about how to implement this BFS in a distributed memory setting, right? So distributed memory, all of you are familiar, right? It's basically each processor has its own memory, right? And then there is some interconnection network, yeah, which connects all these processors together. So what's the critical thing over here? Well, you can't directly access the memory of another processor, right? So what you actually have to do is you have to send a message to the other processor requesting for the data, and the other processor will send the data back, right? So you have to use send and receive calls in if you want to do this, right? Well, architecture is also evolving. So now there are mechanisms where you can directly get data from another memory, right? So if P1 wants to get data from the memory of P2, what happens is that it sends the data to processor 2. There's a DMA controller here. And what it basically does is it recognizes that it's not a normal send receive request. You have to explicitly say that you're directly accessing data from the memory. And this DMA controller will then fetch data from that memory, whatever data is required, and send it back, right? Bypassing the processor 2. So that processor 2 does not need to intervene. Because when you do a send or a receive, if you're doing a send from processor 1, then processor 2 has to do a receive operation, right? So processor 2 is also involved in that communication, right? So anyways, so we are going to stick to the traditional send receive calls, okay? And we are going to work in the MPI framework for now, all right? Okay, so coming back to distributed BFS, right? So if you're working on distributed memory systems, the very first thing you have to decide is how are you going to distribute the data? Okay. And typically there are two kinds of distributions that are used for graphs, the 1D distribution and the 2D distribution, okay? So we'll talk about both of them. Both of these can be implemented using adjacency lists or adjacency matrices. So what is the 1D distribution? The 1D distribution is essentially that you just partition the vertices, Okay. So what you'll do is, if this is your set of vertices, let's say there are n vertices, right, and p processors. So you're just simply going to give n by p vertices to each processor. What does that mean, giving a vertex to a processor, right? Essentially, what it means is that that processor is going to maintain all the additional information that is required for that vertex. Okay. It is going to maintain the adjacency list, any other attributes that are there, all of those will be maintained by that particular processor, right? So we'll have some function called owner, right? So when we say owner of a vertex V, this is going to return us a processor ID. Or in terms of MPI, we actually call this a rank, right? Rank is nothing but processor ID, similar to thread IDs. When you start a distributed job, each node or process is going to get a unique ID, and these IDs will run from 0 to total number of processors minus 1. Okay. Similar to thread IDs. So we have this owner function, right? And we've equally distributed the vertices amongst the processors. That may not always be the best way of distributing the vertices. For the purpose of load balancing, you may want to distribute it a little differently. So maybe the first few vertices have very high degree. Maybe these are sorted in order of degrees or something, right? So that the load becomes imbalanced. In that case, you can, just randomize the IDs and then distribute them, right? That's one way of doing it. Another common technique that is used is, typically what happens is when you have a graph, you perform many different operations on the graph, right? Not just breadth first search, not one algorithm. So typically you want to store the graph in a way that is suitable for all different kinds of algorithms. So again, the 1D distribution is one way of doing it. Another common thing that people try to do is that they try to partition the graph carefully, right? So here's an example. So let's say that, these are some vertices, right? And then there are these two edges going across, right? And let's say that, yeah, this is some dense part maybe. Okay. So what they'll try to do is they will try to basically identify some dense clusters in this. So they try to identify a cut, or basically a partition, that divides the graph up into P parts, right? As much as the number of processes, right? So that each of these parts is dense and you minimize the number of edges in the partition, right? So essentially minimize edges in partition, right? That means the edges going across the clusters. Well, theoretically, this is a difficult problem to solve, but in practice, there are packages like Metis is one package you'll come across, which is used very often, right? Particularly for graph problems. There are others as well. These use heuristics, obviously. There are no guarantees, but they do pretty well in practice. And they try to come up with these partitions, and then you give one of these partitions to process one of these partitions to process two, and so on. Right? That's the way you do it. Well, for some algorithms, this turns out to be better, right? Because most of the communication is then intra-process communication, right? You don't have to send data across from one node to the other node, right? Because that is expensive, right? Going across this interconnection network is not cheap, right? That's where most of your delay comes, right? So you want to minimize that.